So far, we are able to delete the head node of our list, or the beginning of the node, or the first node, and we are also able to delete the tail node, or the last node of our list. In this video, I'd like to be able to delete a particular node at any index, whether it's index 1, 2, 3, or 4. Let's first start by creating a function prototype. This function is going to be a node type, and we're going to call it pop index, and it's going to take in two parameters. The first parameter is going to be a double pointer. For our head, we're going to use call by address, and the second parameter is going to be the index that we want to pop. I'm going to copy this function prototype and put it at the bottom and create a definition for it. Before I start coding, let's go over to the right hand side of the screen so we can talk about the logic for this function. Here I'm going to go ahead and create an activation record in our stack for pop index. Like our push tail function, we want to have a current pointer and a temp pointer. So here we're going to have three pointers. We're going to have a head pointer, we're going to have a current pointer, and we're going to have a temp pointer. And the temp pointer is what we are going to delete. We also want to have an integer counter, I, and we're also going to have a numNodes integer variable. And for our number of nodes, we are going to use our function that we've already created, the count nodes, which already counts the number of nodes for us, and we're going to store that value into numNodes. And I is simply going to be our index counter, so that we're able to have our current and temp traverse and stop at the particular index that we wish to delete. Each of our pointers will currently be pointing to the first node of our list. And let me go ahead and type these pointers and these variables in our code. Our first pointer is going to be our current, and we're going to set that equal to asterisk head because we have a double pointer here. A double pointer is a pointer to a single pointer. Basically, a double pointer holds the address of a single pointer. We're also going to create a node temp, and we're going to set that equal to our head pointer. We're going to create an integer, I, and we're going to set that equal to 0. And finally, we're going to create an integer called numNodes for number of nodes, and we're going to set the value of what our count node function returns. And inside of there, we want to put the asterisk head because we have a double pointer in our parameter. And this creates all of the pointers and integer variables that we have inside of our pop index activation record. The first condition that I want to target is always to determine whether or not our list is empty. And again, how do we determine if our list is empty? Easy. If our head is equal to null, or if our head is null. Asterisk head equals null. Then all we want to do is printf the list is empty. And then we simply want to exit our function with an exit 0. Let's go ahead and test this condition. And let me comment out all of the function calls. To call our pop index function, we need the address of head. And we also need the index of what we want to pop. And in this case, it doesn't really matter, so I'll just put 1. And let's see if this works. The list is empty. So our first condition worked. The next condition is if our list has one node. Let's address that condition. Well, how do we know if our list only has one node? I'm going to draw it here on the right. So here at the bottom, let's just say we have 40 here, and then we have our next value, and then we have our head node, and I'm just going to abbreviate our pointers, our current node, and our temp node, all pointing to our head node. Well, if the temp's arrow next is null, then we know we only have one node. So what we want to do, if that's the case, is we just want to pop that or delete that only index and set all three of these pointers to null. So let's go ahead and code that. And that's very similar to how we coded our pop tail function. Else if temp arrow next equals null, then we simply want to free temp, and then we want to set temp to equal null, and we want to also set current to equal null and our head to equal null. Let's test this condition. So here I've already uncommented our first node, which is 40, and we want to pop index 0 in this case. So the list is empty. Let me go ahead and add the print statement. And it's the same print statement that we use for our pop tail function. And I'm just going to copy and paste it here on line 71. So that way we know what index node we're popping and what data we're popping. And in this case, we should be popping 40. So let's go ahead and run this. There it is. So node index 0 and data 40 was deleted. And now our list is empty and we have no nodes. Our third condition is, what if we want to pop our head node? We want to pop the first node. So if we want to delete the first node, let's go over on the right so we can talk about the logic. If I want to pop index 0, what I want to do is I want to traverse head to current's next, which is 0, 200. So I want to traverse head. After I traverse head, I then want to assign this address to current. And once I do that, current will now be pointing to head. And notice how temp is still pointing at our first node. So now that we have our head and our current pointing to the second node, we can now free temp. Now in this case, order matters. If we free temp while head and current is still pointing to it, we lose this link right here. And we will have memory leaks in our heap. And so that's why it's important to first move head and then have current follow it and then free temp. So let's code that. So there are two ways that we can code this condition. We can either say if index equals 0, or we can just say if I equals index. And let's do that. Else if I, because we know I is currently set to 0, then we want to traverse head to current's next node. And then we want current to follow head. So we want to assign the address of head into current. Then we want to free temp or delete the first node, which temp is pointing to right now. And we don't want to have a dangling pointer. So we want to set temp to null. Let's test this condition. Index 0 is 40. Number of nodes 1. Let me put a print list here so that we can have a before and after. So here is our first list in which we have 2 nodes. And then after we popped index 0, which is a 30, we have 1 node. Let me go ahead and delete this. I'll just add a print statement like we did with our other functions. So that way we know what we popped. And that print statement is going to be the same as this print statement. So let me just copy this. And you want to put it right before you free the temp. All right, so let's run this again to make sure that it works. And there it is. Data 30 was deleted. So let me uncomment these other function calls and let's run it. So there it is. It deleted the head node. Let's go ahead and add our error check. If an index that is out of bounds is requested to be deleted, if it's less than 0 or more than 4, we're simply going to print the request is out of bounds. So here's the logic. If index is less than I, in this case, if it's less than 0, or index is greater than the number of nodes minus 1. And we want to put minus 1 because our index starts at 0, whereas num nodes, it starts counting at 1. And so they have to match in terms of whether or not they're equals. 1 minus 0 is 0. So that's why we have to put a -1. So if this is the case, we want to printf index request is out of bounds. For the first format specifier, we want to do I. For the second format specifier, we want to do num nodes minus 1. And then we just want to go ahead and exit 0 and exit the function. Let's test this condition. Here I'm going to request -1. Oh, I misspelled print. Now let's test this condition. Index request is out of bounds, must be between 0 and 4. Let me put 5 here. Index request is out of bounds. Our error check works. So let's address our final condition. This is the part where we can pop a node at a specific index. Let me go ahead and return the arrow of head and current back to our head node. And let's talk about the logic. So say we want to pop or delete index 2. What we want to do is we want to be able to use our I variable. And so I'll write that here. And then our index that we want to pop is 2. And I starts at 0. So what we want to do is, as long as I does not equal index, we want to set the temp's address in the current, and in this case it already is that since it's our first node. And then we want to traverse temp to our next node, and then we want to increment I with I++. Let's traverse the rest. I is currently a 0 and I does not equal 2. That's a true statement. We're going to assign temp's address to current, and then we're going to move or traverse current to the next node. Temp will now be holding the address of 0x200, and then we're going to increment I with I++. I will be 1. And again, the index that we chose to pop is 2. Well, 1 does not equal 2. That's a true statement. And so we go through our condition. Again, if that's our true statement, we want to assign temp's address to current. And so current will follow temp. So current now holds the address of 0x200. And then we want to traverse temp to the next node. And after we traverse temp to the next node, we want to increment I with I++. So now I is 2. 2 does not equal 2. Well, this is a false statement. And so we break out of the loop. But notice how current is always tailing temp. So that's why order matters. We want to make sure that current is always behind temp. We just don't want to free temp, because if we free temp, we lose this link right here. The link, the 0400. So we will have memory leaks. The first thing that we want to do before we free temp is we want to set currents next and assign it to, or we want to assign temps next to currents next. So we want to have current, we want this pointing to here. And then once we have that pointed to there, notice how it's all linked up now. We can free temp and then set temp to null. Let's code this. Else, since we're traversing, we're going to use a while loop. While I does not equal index, and we want to assign temp's address to current, so that way current is always tailing temp. And then we want to traverse temp by setting it to temp arrow next. And then we want to increment I with I++. And once this condition becomes false, we want to exit out of this while loop. So when we exit out of this while loop, this is when we want to first set currents next, because we don't want to lose that link, or we don't want to lose this link. We want to say current arrow next and assign temp arrow next to it. And as soon as we do that, we can free temp. But let's go ahead and add our print statement here. After we print what temp is currently pointing to, or the data, we can free temp. And then we want to set temp to null. Let's test this condition. Let me just go down the whole list. Let me do -1. We should get a out of bounds. Made an error. It should be arrow next. Let's see if I have any more errors. Hopefully not. There you go, out of bounds. And let's pop our head node. Index 10 was deleted. A quick note on popping our head node. If the list has one node, or if we want to delete the first node, we can simply call our pop head function if we wanted to do that. Let's go ahead and delete index 1. Okay, I have an error. This is the error that I made. I put the order in the wrong place. It should be exclamation equal. Let me go ahead and fix that. And now let's test it, see if that works. So let's go ahead and pop or delete index 1. Index 1 would be 20, so it deleted 20. Let's go ahead and delete index 2. And index 2 should be 30. So index 2, data 30 was deleted. Let's go ahead and delete index 3. And index 3, which is 40, is deleted. And notice how when one node is deleted, we go from 5 nodes to 4 nodes. And let's go ahead and delete our tail node, index 4. And then if we go to index 5, we should get an out of bounds. As far as time complexity, the best case scenario is O of 1, constant. If we're deleting the head node, then that's constant. But if we're deleting any particular index and we have to traverse to each node, then that's going to be O of n. And like our other functions, we can also write this function as a return by address. So let's go ahead and do that. And again, very simple modifications. So let me copy this function prototype. And since we want to do a return by address, I'm going to put a 1 at the front and turn this into an address node data type. I'm going to delete a asterisk from the head. I'm going to take this function and I'm going to copy it and I'll put it right below it. And again, change the name to pop index 1. Make this a pointer. Remove an asterisk. And now, since we did that, anywhere you see a head, remove the asterisk in front of it. And then at the end, all we're going to do is we're going to return the address of head. And let me just make sure that this compiles before I draw the pictorial representation. And here, I'm just going to comment this out. And here, let me call it. So pop index 1. I'm going to pass head and 1. And let's test, well, let's test the whole thing. Let's do -1. Again, I forgot to remove that. Out of bounds, request must be between 0 and 4. Let's pop the head node. Index 0. Index 1. 2. 3. 4. And 5, which should give us an out of bounds. Now let's use both functions simultaneously. Let's pop index 2 and 3. So there, our index were popped. What's happening here is on the right hand side, this head pointer in our pop index has its own address. And when we call the function in line 44, when we have this pop index, what we're essentially doing is we're returning the head address. And so this is an address. So this is the same thing as head. And we're assigning 0x50. So whatever address, let's just say that this used to be 0x40, this will now be 0x50. This head basically becomes this head. And that's our pop index function, both call by address and return the address. Thank you for watching.